So we are going to do some more problems on this chapter on homomorphisms and factor rings before we complete this chapter. And as I said before, this is going to be our last topic in the entire course on groups, rings and fields. So let us start with our problem today. The problem which we are going to try first is find the values of n such that Zn contains a subring isomorphic to Z2. So you know that Zn is the set 0, 1, n minus 1, and any subring of Zn isomorphic to Z2 will be of the form 0, let us say S, because Z2 contains two elements, so this subring also should contain two elements such that S plus S is equal to 0 and S times S is equal to S. This is because this should be isomorphic to 0, 1, where 0 plus 0 is equal to 0, 1 plus 1 is equal to 0, 1 times 1 is equal to 1, and 0 times 0 is equal to 0. So this is S times S, and this is S plus S is equal to S. This is 0 and this is S. Where 0 less than S less than N. See here, addition and multiplication on Zn are mod n. So if S plus S has to be 0, then this n has to be an even number. If S plus S is equal to 0, then n should be an even number. Say n is equal to 2m. Then only we can have this mod n. So we still need to find out, can we take any even number? So if you take, let us continue taking the even numbers like this. So what we do is, let us say, so m times m, or m plus m is equal to 0. That is 2m is equal to 0 because of this, right? Because we are taking mod n. So here 2 times m, if m is equal to 2, this is 0. 3m is equal to 2m plus m, and that is m. So if you take 3m, so if m is equal to 3, then this is satisfied. 4m is 0, 5m is equal to m, 6m is equal to 0, 7m is equal to m. That is, when m is equal to 1, 3, 4, 3, 5, 7, dash, 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 then s times s is equal to s is satisfied. So, the values of n are even numbers of the form n is equal to 2m, where m is odd. So that is so those are the values of m for n such that there exists a subring isomorphic to Z2. That is actually starting from Z2, that is when m is equal to 1, then Z6, then Z10, these are all contains a subring isomorphic to Z2. So our next problem is this: give addition and multiplication tables for the factoring 2c over 8c, and show that 2c over 8c is not isomorphic to Z4. By the way, this contains 4 elements, so it is a ring of 4 elements. Still it is not isomorphic to Z4. So what does this factor group contain? 2z over 8c contains 8c, 8c plus 2, 8c plus 4, and 8c plus 6. These are the elements. So if you want to complete the addition and multiplication table, 8c, then 8c plus 2, 8c plus 4, and 8c plus 6. Here 8c, 8c plus 2, 8c plus 4, 8c plus 6. And that is addition, and the multiplication is also going to be same number of elements in the table. Addition 8c, 8c plus 2, 8c plus 4, 8c plus 6, 8c, 8c plus 2, 8c plus 4, 8c plus 6. See, this is very similar. It's actually mod 8. Here also it's mod 8. So this is going to be, this is our 0 of the element. So this is I'm not going to fill the whole table. I will fill some of them, and you can fill it up. This is going to be 2c plus 4, 8c plus 6, and here also 8c plus 2, 8c plus 4, 8c plus 6. Let us compute a general element, say 8c plus 4 and 8c plus 6. Let us compute this element. So this is going to be 8c plus 4 plus 6, it's 10, So that's going to be 2. Similarly, you can compute all of this. Here also it's going to be the same, but here it's a multiplication. So this is a 0 additive identity. So these are all going to be the zeros. Here also going to be zeros. Then let us compute one general element just like this. So this is going to be 8c plus 6 times 4 is 24. 24 mod 8 is going to be 0. So that's it. Okay. So, and so let us take one more here. Say let us take this one. This is going to be 8c plus 4. So this is the multiplication table. Why this is not isomorphic to Z4? Actually, if you take the addition, this part is isomorphic to Z4 as a group, because if you take the table, you will be filling the same way as this in a Z4. But here it is different. Here 2z our 8c does not have a multiplicative identity, but Z4 has a multiplicative identity, and that implies 2z over 8c is not isomorphic to Z4. So Z4 is equal to 0, 1, 2, 3, and 1 is the unity of Z4, the multiplicative identity. So we don't have a multiplicative identity here. If it is, it has to be 8c plus 1, and that is not in here. So our next problem is this. Let phi from F to R be a ring homomorphism. Where F is a field and R a ring. Then phi is either 1, 1 or phi of x equal to 0 for all x in F. Meaning it is a trivial, either trivial or 1, 1. So assume, this is an important result by the way, when you study the field theory more. Assume that n is equal to phi of kernel of phi. That implies n is an ideal. Right? Now, let n is different from the trivial subgroup. Implies phi is not 1, 1. What we need to prove that if it is not 1, 1, then every element in F is mapped to 0. That means there exists an A different from 0 belongs to M, and that is actually contained in contained in F. And since F is a field, A inverse exists, and that implies A times A inverse belongs to N, because N is an ideal. the definition of the definition of ideal is an is contained in n and nb is contained in n. Here this is our A and this is our A inverse, and that should be 1, and that should be an element in n, and that's what this one is. That implies 1 belongs to n. So 1 belongs to n implies for every x belongs to f, 1 times x belongs to n, and that implies x belongs to n. So that implies n is equal to f, and that implies phi of x is equal to 0 for all x in f, because x is in f, so x is in n is the kernel, so it is actually mapped to 0. So if it is not 1 1, every element is mapped to 0. The next problem is this. Let R be a commutative ring with unity and is of characteristic or is of prime characteristic P. Then the map phi from R to R defined by phi of A is equal to a to the power of P is a ring homomorphism. This is very simple, because since R is of characteristic P, where P is a prime number, A plus B to the power of P is equal to A to the power of P plus B to the power of P, because if you expand using binomial theorem, every element between these two will collapse because it's of characteristics P. So all we need to do is phi of A plus B is equal to A plus B to the power of P, and that is equal to A to the power of P plus B to the power of P, and that is equal to phi of A plus phi of B. And phi of AB is equal to AB to the power of P, because it is commutative ring, this will be A to the power of P times B to the power of P, and that is equal to phi of A times phi of B. And that implies phi is a ring homomorphism. Our next problem is this. Let phi from R to R prime be a ring homomorphism and n be an ideal of R. Then phi of n is an ideal of phi of R. So we need to show that R prime times phi of n is contained in phi of n, and phi of n times R prime is contained in phi of n for all R prime in phi of R. So what we do is you take an element from here, then show that it is contained in here. So let n prime belongs to phi of n and r prime belongs to phi of r, and that implies there exists n belongs to n and r belongs to r such that phi of n is equal to n prime, phi of r is equal to r prime. Now n is an ideal of r implies nr belongs to n and Rn also belongs to n. That implies phi of nr belongs to phi of n and phi of Rn also belongs to phi of n. And this is actually phi of n times phi of r belongs to phi of n, and phi of r times phi of n belongs to phi of n. And this is n prime and this is r prime belongs to phi of n, and this is r prime, this is n prime belongs to phi of n. And that implies phi of n times r prime is contained in phi of n, and r prime dash phi of n is contained in phi of n, and that implies phi of n is an ideal of phi of r. Our next problem is, let R be a commutative ring and IA is equal to x belongs to R such that AX equal to 0. Then IA is a ideal, is an ideal of R. So what are the things we need to prove? We need to prove IA is a subgroup of R, then IA is closed under multiplication. That's all we need to do, and so that means IA is a subring. Then we need to show that R times IA is contained in IA and IA times R is contained in IA for all R in R, and this implies IA is a ideal. So these are the three steps. So we'll quickly go through these steps. So IA is a subgroup. So verify identity belongs to IA, which is true actually, 0 belongs to IA. Then inverse of every element of IA belongs to IA, and of course IA is closed under addition. So here actually 0 is the 0 belongs to IA. 0 belongs to IA. 0 belongs to IA because A times 0 equal to 0. and the inverse of A in IA is minus A, and that also belongs to IA. And if you take two elements, let x comma y belongs to IA, implies AX equal to 0, AY is equal to 0, implies AX plus AY is equal to 0, implies A times X plus Y is equal to 0, and that implies X plus Y belongs to IA, implies IA is closed under addition. Now IA is closed under multiplication. That implies let x comma y belongs to IA, and that implies AX equal to AY is equal to 0, and that implies AXY is equal to AX times Y is equal to 0, and that implies XY belongs to IA. So IA is closed under multiplication. Now we need to show that it's an ideal. So let R belongs to R and X belongs to IA, and that implies R times, that implies AX belongs to S equal to 0, and that implies RAX equal to 0, and that implies RA belongs to IA, and that implies R times IA is contained in IA. Similarly, IA times R is contained in IA, and that implies IA is an ideal. So our next problem is any factor ring of a field F is either the trivial ring 0 or isomorphic to the field. Okay, so either it is the trivial ring or isomorphic to the field. So let us see, if you want to find out the properties of a factor ring, we'll start with an ideal. So let N be an ideal of a field F. So we need to find out F over N, right? The claim is that F over N is isomorphic to 0 or F over N is isomorphic to F. This is what we want to prove. This is what we want to prove, right? So let us assume that let us assume that N is different from 0. That is, let A belongs to F and A belongs to N and A is different from 0. There is another element in N that is different from 0. Okay? So that means A inverse exists because A inverse is from F and F is a field. Every element in the field, every non-zero element in the field has an inverse, and that implies A is in N, A inverse is in F, that should belong to N, because n is an ideal. See, the definition of ideal is that an is contained in n and b is contained in n. Right? So we are taking this one. This is coming from n. Sorry, we are taking this one. This is coming from A, and A inverse is coming from F. And if you multiply this, this should be in N. That implies 1 belongs to N. And that implies 1 time R belongs to N for all R in F. That means n is equal to F. And that implies F over n is 0. Because they are same. Now, if F, so let n is equal to 0. This is when n is different from 0. This implies that F over n is equal to F over 0, and that is definitely is isomorphic to F. So, F over n is either isomorphic to 0 or F over n is isomorphic to F. So, we will do one more problem before we complete this chapter on homomorphisms and factorings. Let R be a ring with unity. Let n be an ideal of R such that n is different from R. Then R by n has a unity. So our first claim is that 1 does not belong to n, where 1 is the unity of R. Why it does not belong to n? Because if 1 belongs to n, that implies R times 1 belongs to n for all R in R, implies R is equal to n, which is not true. N is different from R. Now the next claim is 1 plus n is the unity of R by n. Okay, so we'll take an element from here. Let R plus n belongs to R by n. That implies R plus n times 1 plus n is equal to 1 times R times 1 plus n, and that is equal to R plus n. And that implies 1 plus n is the unity of R over n. The reason for us to prove that 1 does not belong to n, because if 1 belongs to n and if 1 plus n is the unity of R by n, then the additive inverse, additive identity and the multiplicative identity are going to be the same. In which case R will become n, and that is not true. So that is why we want to show that R does not belong to n first. Then show that 1 plus n is the unity of n. Then the additive identity and the multiplicative identity are different, so that R will not become n. Okay, so that is a proof of the unity of R by n. So with this problem we are coming to an end to our entire course on groups, rings and fields. I try to cover the syllabus of Calicut and Kannur universities as much as possible, and I hope the series of these lectures are going to be helpful for you to prepare the exam. Thank you for watching my lectures.